Hello and welcome everyone. Looks like we can start now. Great to have you all on board with the Markham panel today. I'm Conrad from the marketing team in Bundaberg, Australia, and we've got Martin Prestige and Doug Hamlin joining us virtually from the Napier office. Martin, could you tell the audience a bit about yourself, a bit about your role at Markham?
Thanks, Conrad. Hello, everybody. Yeah, Martin Prestige. Been with Markham for 13 odd years. Only work in the civil infrastructure space, remediating concrete projects, a lot in the marine sector, bridges, wharves, tunnels, any large lumps of concrete, really. Thanks for coming along today. I'm no expert on the carbon movement, but just a few things we've picked up along the way. Thanks, Conrad.
Thanks for that, Martin. That's great. And what about you, Doug?
Yeah, I'm on similar lines of Martin. So I work in the infrastructure industry space here at Markham. So that's adding service life to existing and new structures, and also involved in the bit of the technical validation side of things. And yeah, likewise with Martin, I haven't got a degree or anything in carbon emissions, that type of thing, but it's some thoughts and really a thought-provoking session, I guess you call it. So yeah, back to you, Conrad.
Thanks for that, Doug. Today we're talking about the concrete carbon challenge and what this involves and some practical responses. I'll be hitting our panelists with some questions about the practical challenges and their experience in the field. We will open the door for guest questions later in the presentation, so please use the Q&A button at the bottom to answer your questions as we go along. So, Doug, to kick us off, could you tell us what we mean when we talk about the concrete carbon challenge? What's the context around this issue?
Yes, sure thing. Thanks, Conrad. So, yeah, it really bears on the science around the carbon emissions. That's at the heart of this climate change topic. For concrete, it's a well-known issue. It's been highlighted a few years ago now, that it's the manufacture of the cement itself that is the bad boy, or is the biggest contributor, if you like, to the carbon emissions of the overall concrete production. The Australian Cement Federation, you can see they confirm that it's the process that generates the most carbon dioxide. So that's when they're making or manufacturing the cement. There's a lot of heat required in the kilns to convert that limestone into clinker and then into the finished product, cement. So yeah, that is the kind of the major factor that contributes to the carbon emissions here. And there's been, I think, one or two studies on that as an overall contributor. It's around about 8% of the world's total emissions, or that's what it's alleged to be. So yeah, it is a significant amount for for one product, one material, if you like. But yeah, that makes sense.
Yeah, it does. That's a pretty heavy amount. So what would we use if we removed concrete from the equation?
Yeah, that's a great question, and it's a very real challenge. Obviously, concrete, I mean, it's everywhere. You don't have to look too far to see some. It is a very robust, it's a durable, it's very versatile material, so you can use it for so many different applications, basically right from floor to walls to ceilings to roof. Well, it's quite dynamic in that way. So it's quite a challenge to find something that replaces it entirely. So as a building material that's more carbon friendly, that replaces concrete entirely. Obviously there's a move to use more of the things like timber in structures. Obviously that's fairly, it's been going for a few years now, but it's still fairly early days. It's not as versatile, so you can't use it everywhere where you use concrete. And the data around the longevity for like a high-rise building or something like that there is starting to build up that data, but there's not a lot known there at the moment. And then the other thing, from a personal point of view, the carbon. Forests is used to sequester carbon and offset that carbon emissions. So yeah, I would raise that question. Is there actually enough renewable forests out there to about a mill it and use that timber in the construction industry? So, like I say, I'm not an expert on this topic, but it's kind of questions that I raise with and think about. So yeah, that's probably the main couple of points there. If you don't use concrete, what do you use? Any other points on that?
I think you covered it well. I mean, timber's making good ground. There's a few other things the concrete companies doing that we'll get into later to save on cement use. But I think the reality is concrete is always going to be with us, some shape or form.
Yeah, that's good. So what other factors should we be considering?
Yeah, so if we go back to the concrete, as Martin said, it's going to be with us for a long while yet. I think we really need to look at that bigger picture. So look at the entire life cycle of a concrete or a concrete structure. If you look at it that way, it does have a low embodied energy per unit of mass. That means the carbon involved in transport, that type of thing, is not really high. If you think about a concrete plant, they're generally fairly close to a construction site. And that's just one example. And so you can reduce down that overall impact. While the cement might be quite high, that is something to consider, and the fact that it reduces the overall contribution, if you like. Martin, have you got anything, thoughts on that one?
Yeah, thanks, Doug. I think what you're highlighting, 8% of the world's emission from concrete shows it's a carbon expensive product to be using concrete. And if we look at, I think we probably need a mind shift on using it more wisely. So the service life of the structures, the longer we can extend the service life of the structure, the overall carbon impact reduces down. So if you're going to be spending carbon expensive, if you like, material like concrete, to be able to produce an end product that lasts, start challenging some of the service lives, push it out to 100 years, 150 years through some of the more newer technologies, some of the air fixtures, that kind of thing. And on the same token, existing concrete structures that are already in place, being able to keep them, keep the longevity, keep the service life extending past where they might have been designed for by applying some newer technologies. If you look at the expansion of the global population, there's a shortage of infrastructure globally. So the environmental impact on having to knock down, rebuild existing infrastructure, as well as keeping up with the expanding global population, anything we can do to extend the service life of existing concrete structures has to be contributing positively to carbon impact.
100%. And if you think about that in terms of, I'm assuming most people would have seen a concrete structure that's deteriorating over time, might be 40, 50 years old. If you think about not only the monetary cost, but the carbon cost to replace that. For one, you've got to get rid of the old concrete. Some of it might be able to be recycled, but what happens to the rest of it? There's the emissions and that associated with the demolition, and then you've got to rebuild that structure. And I'm obviously talking worst case here, but you've got to use a whole lot more new concrete. So we need to really shift our focus to looking after what we've got in terms of infrastructure, and then if we do build new infrastructure, make it do something right at construction phase to ensure that you get concrete life. I think you got a few thoughts around the, that maybe not just hitting code. You might really push it a bit further. New concrete.
Yeah, I think so. So often because of cost constraints for developers as head owners, which is a legitimate restraint, they're often meeting just code. Now the codes for concrete structures are great for their durability, but there is more that can be done. So if you take it past the code for a little more expenditure, we're not talking a lot. They talk about spending $1 during construction, saves $125 during the remediation phase further down the track. So, spend a couple of extra dollars during construction, putting in some admixtures, some surface treatments, that kind of thing, that would just extend that life cycle. There's a huge impact over the lifespan of the structure.
Yeah, that's good. That's good. And that also obviously there's a lot of things that goes into concrete construction, like the design, the mix design, that type of thing. What we are seeing from a lot of the major ready-mix suppliers is that they're wanting to, reduce the overall cement consumption. Obviously, that's a major contributor. And it really brings up another topic of take for example a wharf project or a bridge for that matter. The code for that bridge might say 50 or 60 MPa bridge will give you a 50-year design life. What we really need to look at is the actual strength required structurally for the project. So to take the loads, that type of thing. A lot of the time, it's only around that, between 30 and 40 MPa that is required. Obviously, concrete's got a very, very good compressive strength. And so what there's quite a shift in focus to look at using, say, a lower MPa concrete, but working with that mix to get it to perform as good as a 50 or a 60 MPa concrete in terms of durability. So yeah, that's really a question or a challenge really to engineers or asset owners to think about that when you're looking at new infrastructure or new build. So can we actually reduce that MPa and work on a performance specification rather than just sitting to code? Because we're not bagging the code, but in reality, there's a lot of structures that are built to code, and we go back and remediate them for concrete corrosion. Is that not too harsh to say?
No, I think every structural engineer would agree that you can build to code, but you've got to monitor from day one pretty much, and we're getting called back earlier and earlier to jobs. That's just the way the trend is going. But I think just put a plug in for concrete companies. So traditionally their role has been to sell as much cement as possible. They are all actively pursuing ways they can bring their cement and still provide the same service to them. So like you say, if you can dial up a project, you say you only need a 35 MPa to satisfy the structural requirements of the project, it becomes extremely expensive carbon-wise to take it to 60 just to keep, say, chlorides or environmental contaminants out, when you could do that with a very carbon-low impact admixture or something like that. So there's definitely advances being made.
Yeah, no, 100% second that. That's a lot of the people we talk to are working at ways to reduce that. So yeah, do you want to say something on some of our newer? Obviously, we've got a range of admixtures for concrete protection. That's what we do. But some of our newer admixtures we're working with, Martin, they do have even lower impact. I'm going to run us through a little bit, the admixtures for a start, but the new ones.
This slide, Conrad, I've shown the hydrogel.
Just get the slide open, you say?
Yeah. Yeah, that's fine. Yep.
Yeah, thank you very much. So As a company, Markham, our main technology is using colloidal silica, and we either spray apply that to the surface or add it as an admixture into the concrete. The picture you've got up there is showing the network of the vein system in concrete. One of the issues with concrete, or the main issue with concrete, is the permeability, so it lets moisture in and out. Now, just about every issue with concrete that's going to shorten its design life is due to moisture being able to be carried in and out of the matrix of the concrete and taking the contaminants in with it. Just the nature of concrete, when the bleed water comes out, these network systems, the moisture can get back in. If we can fill those porosities, capillaries, block them up, we're stopping moisture and contaminants getting in, we're extending the life of the concrete, we're taking moisture, oxygen out of the equation from a corrosion, but also for the more expensive ASR, DEF, the other common issues that we have with concrete, they're all moisture fed. So what the product does, talking existing now, we just clean the surface down, spray apply colloidal silica. It gets down, carried down in the colloidal form, down into the porosities, mixes, reacts with the calcium hydroxide and forms a gel into a solid state, blocking those capillaries off. We can do the same thing as an admixture, so going in at the start of the project in the back of the truck and getting that colloidal silica right through so that the gel forms and the porosities are blocked from day one. Did you want to say something about the actual impact of the colloidal silica itself?
Yes, so thanks for that overview. So if we're talking about admixtures to concrete, so typically there's with colloidal silica, there is some carbon emissions associated with it in terms of the heat required to manufacture them. Now they are, if you look at that, even if you take that into account, because you're only using 1 to 2 litres per cubic metre of concrete, even though it has some impact, that is even less when you take it over a whole cube of concrete per se. So if you and it's obviously a whole lot lower than the cement itself's carbon impact. So what we've as a progression on that, we've actually started working with a company right here in New Zealand that harvests the colloidal silica right from the geothermal fluids that's used for power generation. Now this is silica that, if it's not taken out, actually works to clog up the pipes and reduces their capacity, so the overall power generation capacity drops. So being able, with this company harvesting that silica out of the colloidal silica out of that fluid, is not only helping the power company, but it also means that it's a very, very low impact or carbon impact for the raw material. So we're able to take that, bring it back to our head office factory in Napier, tweak it, modify it, and make it do what we need it to do in concrete, and then use that to put into new concrete, and as Martin's discussed, the waterproof that fill up those pores, porosities, so that moisture can't get through the concrete, and therefore pushing that that service life out of the concrete structure. So yeah, is that making sense?
Yeah. So it's an exciting product. Like I say, it's actually been harvested from steam that's coming out of the ground. You can't get much more environmentally friendly than that. But when you put it up against some of the other products that they're using to replace cement, so cement's obviously the bad boy, but then you've got microsilica, fly ash, they also have a lot of carbon impact. So, and then you can replace those with colloidal silica. You're dropping the carbon footprint of the concrete structure considerably by getting the same performance.
Yeah, is that making sense, Conrad?
Yeah, that's it's very interesting actually. I can see how that approach would save time, because after all, making the structure last longer is reducing its lifetime environmental impact. You don't need to rebuild a structure and use more cement. Appreciate you taking the time to help us with that. We've got some live questions just come in. One is, could you give more details on the practices or processes you are using to extend the service life of concrete? In terms of percentage using the processes you're using now, could you estimate by how much could the service life of a structure be extended?
Yeah, thanks, Madam. That's a great question. A lot goes into the service life of a structure. So there's obviously the environment that the structure's in, and then the construction methods, that kind of thing. So it's hard to put a percentage per se on how much we can extend the concrete structure, but life cycle. But if you take it over against a standard bridge structure, you know, we offer 25 years, 50 years. We're involved in a job that we did in for the Brisbane port, where it was involved with a 100-year design life. We're working with Dennis on a similar job. So yeah, it all depends. It's hard to, we're a very project specific company. So we'd like to get involved at the specification stage and just see what you're trying to do, whether it's in a marine environment, whether it's under some sort of chemical attack in an industrial situation, and then we can answer more categorically what you'd hope to achieve.
Okay, thank you. There's the next question is, do you have products which would save, say, deteriorating old concrete buildings and give them new life, new use?
Yes, yeah, definitely. So there is, obviously we've talked a lot about the admix for new concrete, getting it right from day one. But yes, there's a lot similar technology, but it's spray applied to the concrete that can, you know, arrest that deterioration process and hold it in that condition that it is currently. So if it is in a satisfactory condition, or you know, a structure might need a few repairs to get it into a satisfactory condition, we can hold it at that point. And then obviously, as Martin said, it's very project specific in terms of the service life extension. But yeah, we always like to give, you know, a definitive number of years that we can extend that service life. Obviously, we are structural engineers, we are durability experts, so we're talking about in terms of durability, not you know, if the structure is going to cope with the loading, that type of thing. Yeah, is that cool? Next one, Conrad.
Yep. And so there's the next question is it available in Western Australia?
Yeah, so Markham, as Doug said, we manufacture the product here in Napier, partner with our raw material suppliers. We export right across Australia, so we've got offices in Perth, Melbourne, Sydney and Bundaberg. And anywhere we haven't got an office, we definitely travel and have applicators on the ground. Right across New Zealand, the UK and through Southeast Asia.
That's good. That's quite widespread around Australia and Australasia. Is there? Oh, there's another question. How does the admix compare in price instead of using a high MPa mix?
Cost-wise, it's pretty much cost neutral. So you're talking a standard, say 35, 40 MPa mix compared to a 60 MPa mix. By putting our admixture in, you're not putting the price of the project through the roof at all. And probably, I'd like to say potential savings, but if you work on cost neutral, you're great.
Yeah, yes, yeah, we talk about there's a lot of variables as well in every project. Yep. Cool.
Yep. Next question is, where can I find information on how much embodied carbon is in a cubic meter of concrete? Is there a table somewhere?
Yes, yeah, I was actually just looking at it a couple of days ago. If you like to flip me an email, I can ask that question. I can send that link through.
Kind of a debate going on how it's measured as well. It's an interesting topic. Probably haven't got time to get into it now, but there's definitely numbers out there readily available on how much embodied carbon in concrete.
So that's Doug, DOUG .Hamlin, HAMLIN at markhamglobal.com if you want to email him.
Thanks.
There's quite a detailed question on ICF. We may have to answer that on offline.
Yeah, that would be good. Sounds interesting though.
Another question is, I am based in Melbourne construction industry, where we have quite a lot of crystalline admixtures being asked for in a lot of projects. What is the carbon footprint of these? Do you provide crystalline admixtures?
Yeah, I don't know the exact carbon footprint of crystalline products. We work with hydrogel admixtures ourselves, which are kind of a more advanced version of the crystalline. So they're using a smaller nanoparticle and less of it to get the same or better results.
Yeah, I haven't seen the exact numbers. It's powder form. It has to have a high. I mean, the process to generate it is going to have a high carbon. The other challenge with crystallines is the health and safety. So they're actually carcinogenic. So we're seeing a lot of that coming through as well. But yeah, it's a good question.
Yep. Next, the last question I think we've got is, a lot of warehouse projects and large slabs ask for rubber-based curing compounds. Is there a better alternative to this?
Yeah, there sure is. Chlorinated rubber for curing. You can use Silica spray applied in a different format to what we're doing for durability, just as a straight curing product. It's similar to, or it's equivalent to a 14-day water cure. So they spray it on, it gets down, sets up the hydrogel, and it helps hydrate the cement particles, traps the moisture in there during the curing process. And that setting up its hydrogel, it's hydrogenic, it's doing everything you want from it. It's better than the curing compound, that's why we compare it to that, because it actually holds moisture inside the slab for that period. It's a good question.
I think that's all the questions we had. It's very good. Is there anything you'd like to add at the end or finish up on that?
Not for me. Thanks everyone for attending. It's most appreciated.
Yep. Thank you very much.
Everybody, and just reach out if you've got any other areas where it's a big topic. Our tagline is saving the world one structure at a time. So if you've got any ideas how we can improve on this, how we can reduce our own carbon impact and get a bit more exposure, then definitely reach out. Thanks for coming along.
Thank you. Thanks for paneling.